Hey everyone, my name is Andrew Ruffin, and I'm a product manager at AMD focused on launching and growing new Azure services built on AMD infrastructure. In this video, I'll walk you through how your infrastructure as a service choices make a difference in the performance you experience in the cloud. AMD and Azure work together to push the boundaries of compute in the cloud, and you'll learn about the latest options during this video. If you're not familiar with AMD, we're a major hardware and software provider across all areas of compute. And in a data center, where Azure is a leader, we provide primarily EPYC CPUs, Instinct GPUs, Radeon Pro GPUs, and a range of networking and custom products that tie everything together. You as a cloud user don't typically need to worry so much about the hardware. Azure does that for you, for the most part. But you're watching to understand why the underlying infrastructure matters, and when you do have a choice with infrastructure as a service, why you'd want to consider the AMD option to maximize your performance. The Azure and AMD partnership goes back nearly 10 years now, and we launched EPYC in the cloud with our first gen product announced in 2017, powering the LSV2 Storage Optimized Virtual Machine, or VM. Since then, we've executed year after year, now with around 60 different VM series. Azure also launched AMD's first AI-focused accelerator, the MI300X, first in the cloud, as well as the first confidential VMs in the cloud based on AMD EPYC. So, when you do have the choice, how do you know if your VM is powered by AMD EPYC CPUs? Look for the lowercase a in the name. The vast majority of VMs you'll see here have that A that I'm highlighting, from the BASV2 to the NVADS V710 V5. There are a few exceptions, like the LSV2 I mentioned earlier, and the H-series VMs, which have been AMD only since HVV2 was announced in 2019. Outside of these few exceptions, Azure has been really consistent in this naming structure for many years now. So look for that letter A. Now, you may be wondering what all of these letters mean. So here's the alphabet soup we live and breathe every day, so you don't have to. I won't read through all of this, but take a look at the number of VM families and choices you have, and you'll see that it covers just about every workload you might need without having to procure and manage your own hardware and data centers. That's really the beauty of Azure, and this is also the menu of compute that Azure services choose from as well. For this video, we'll cover performance of the most commonly used general-purpose DA, memory-optimized, EA, compute-optimized FA, and the aptly named H-series high-performance computing VMs. Before we dive into the details, it's worth noting the sheer scale of what Azure offers in terms of regions and compute diversity. I regularly count the number of Azure regions available and where you can find AMD compute. And as of my last check, you'll find AMD options in each of the 65 Azure-controlled public regions. DA, EA, and FA families are the most widespread of what we've discussed, with H-series VMs less common but available in some form in every major region. If you're looking for a specific type that's not yet in the region you need, do reach out to your Azure or AMD contacts with what you're looking for. Now let's talk through the performance of the general-purpose, memory-optimized, and compute-optimized VMs. First, what's in these VMs? They're based on the 5th Gen EPYC processors, and the VMs themselves went GA or generally available earlier in 2026. The general-purpose DA family is best for many workloads and comes with either 4 GB of memory per virtual CPU, or vCPU, or 2 GB. Look for that little L in the name for lower memory. If your workload can handle lower memory, you're going to save by moving to a lower memory SKU. These VMs also come with and without local temp disk, so look for the little D to see if there's a temp disk. If you don't need that temp disk, then you can save again by not choosing that SKU. Next are the memory-optimized EA family, which increase the memory to 8 GB per vCPU. This comes with a cost increase, so if your workload doesn't need this much memory, then stick with the DA family for sure. Many workloads benefit from more memory, however, so these can absolutely be worthwhile. Last but not least are the compute-optimized FA family, which come with 2, 4, and 8 GB of memory per vCPU. In this case, you'll get a full core as a vCPU versus a thread, so these are some of the highest performance options you can get without going to specialized compute options like the H-series, which we'll talk about later. These VMs come at a price increase over the corresponding DA or EA series VMs, so it's best to use for bursty workloads or maximize performance per dollar on workloads with core-based software licenses. One option you might consider across the EA and FAM variants is constrained core VMs. This means if you want to keep cores constant while scaling memory and storage, you can do that. This can save significant money on software licenses that charge by the core, and from a performance perspective, you can increase the memory per vCPU from 8 to 1 all the way up to 32 to 1. So how do these different configurations perform? Let's get into it. With each new generation released on Azure, AMD engineering teams benchmark performance across a range of web, media, database, and application workloads, aiming to get a sense for general IT performance for a typical customer. Everyone's workload is different, so these benchmarks may not match exactly what you need, but the idea is to give you a sense for how we are improving generation over generation. Specifically, we test NGINX and Redis for handling web serving and caching, ffmpeg for video encoding transcoding, MySQL for open source database throughput, server-side Java Multimax for multiple users on an application server, and 2 Microsoft SQL Server workloads derived from TPC-E and TPC-H throughput for transactional and analytical database performance, respectively. For our V7 Turin DA series over the prior V6 Genoa DA series, we see on average 28% performance uplift across 7 tests, with a max of 50% uplift for MySQL, an open source database. For Turin FA compute optimized over Genoa FA, we see an average again of 28% performance uplift with a max of 47% for, in this case, Redis. For Turin EA memory optimized over Genoa EA, we see an average of 26% performance uplift with a max of 52% for MySQL again in this case. It's worth noting that the price of V7 VMs is the same as for V6, so performance per dollar is basically the same as what you see here. We're also looking more and more at CPUs as an inference target, where you may not need the throughput of a GPU. Testing on our own servers, we're seeing around 39% faster large language model inference throughput using the open source Llama 3.1 model, around 86% faster similarity search, which is being deployed as a feature in more databases across Azure, like Azure PostgreSQL, and just over double the performance for machine learning workloads represented by XGBoost. When I speak with companies considering Azure or already on Azure, the question almost always lands on, what do you recommend for my IaaS workload? My current guidance is to look for the V7 VMs based on 5th Gen EPYC, fall back to the still very good V6 VMs based on 4th Gen EPYC, and only look to the V5 VMs based on 3rd Gen EPYC if you care only about costs, as these are the lowest cost options among the 4 generations we have. I don't recommend V4 VMs today as they're the lowest performance of the 4 generations and the highest cost, so it's a no-brainer. I'm not showing pricing here, but the performance really is what we care about. So based on Azure published Linux compute scores, we don't see a major uplift from V4 to V5, just 4% give or take. That changes as we moved from V5 to V6, with a 47% uplift for DA and a 48% uplift for EA based on our 7 tests. Going from V6 to V7 brings still very healthy performance uplifts, as we discussed earlier, and at the same cost, so V7 is the way to go if you can. V7 is today in just over 10 regions, while the V6 is much more widespread and nearly 60. So look at where you need to deploy, go for V7 if you see it, make an ask for it, but look at V6 in the meantime for a still great performance experience. Speaking of performance, let's go even higher up the stack with IaaS options for HPC or high-performance compute. Azure has been a leader in HPC in the cloud, launching 5 generations and 6 different VM types since 2018. From HB, which is now retired, HBV2, which is set to retire next year, to HBV3, which introduced AMD 3D V-cache technology, which enables more cache per core, to HBV4, which maintained 3D V-cache while adding more cores and system memory with HX, to most recently HBV5, which is the first CPU with high bandwidth memory for HPC in the cloud, something you can't get anywhere but Azure today. The most recent H-series VMs come with the following ranges of sizes, memory, storage, and networking. I won't read through everything here, but the key differences are that HBV5 has significantly more cores with high bandwidth memory, making it a great fit for computational fluid dynamics, or CFD, for example. HBV4 doesn't have HBM, but it has 3D V-cache, giving lots of high bandwidth local cache. It's a good fit for finite element analysis, or FEA, for example. HX is the same as HBV4, but with double the system memory, making it a great fit for electronic design automation, EDA, a major workload for semiconductor designers like AMD. So how do the configs impact performance? Phoronix, a news and performance website covering open source in great depth, did a large number of tests and published them in an article titled The Incredible Evolution of AMD EPYC HPC Performance Shown in the Azure Cloud. With that title, you'd expect some good results, and across 60 tests, the HBV5 achieved across the geometric mean nearly 5 times above HBV2, over 4 times above HBV3, and double the prior generation HBV4. For some workloads like computational fluid dynamics, the performance is even better. OpenFOAM is an open source toolkit for computational fluid dynamics. In this test, we simulate airflow around a motorbike with 100 million cells. For this test, HBV5 has a 4.8x speedup over HBV4, a 12.3x speedup over HBV3, and over 22x speedup over the HCVM. For workloads that can take advantage of all the high bandwidth memory on the system, like CFD, HBV5 is a great choice. So HPV5 is the newest, but HPV4 and HX are also good fits for certain workloads. Nissan uses HPC to simulate crash testing for their vehicles, and this workload is increasingly important with more regulations and demands for safety. Nissan tested the HPV4 for their compute-aided engineering, or CAE, for crash test simulations, and they found that it provided 30% more performance than their previous cloud provider's VM. This extra performance combined with Azure's pricing helps Nissan save 20%. So, we've covered quite a bit in a short amount of time. For more information, check out the AMD and Azure partner page, the Azure IaaS solutions page, the AMD tuning guide for our VMs in Azure, a new report from Signal 65 evaluating the technical and economic side of HPV5, and more info on the Nissan HPV4 case study. If you have any questions, don't hesitate to reach out to azure@amd.com and we'll help you find what you need. Don't forget to check out our other videos on cost optimization and security and confidential computing. Thanks for your time.